Hello, I am Roel Atienza from the University of the Philippines. I am presenting my paper on improving model generalization by agreement of learned representations from data augmentation. This is the outline of my talk. First, I will give a brief overview of data augmentation. Then I will discuss how to get more out of data augmentation. It is called regularization by agreement maximization, or AgMax. Lastly, I will present the experimental results. In the past few years, we have seen effective data augmentation methods such as cut-out, cut-mix, mix-up, and auto-augment. The key idea is more or less the same. Introduce changes in the input image while retaining the label or a certain percentage of the label during supervised training. Assume that there are two input images with corresponding labels. The first input is an image of a bird. The second one is an image of a cat. X refers to the input while Y refers to the label. In cut-out, we remove a certain region. For example, a black rectangular region masks out an area of the input image. While keeping the label, we force the neural network to learn that it's still a bird based on what is left on the input image. In mix-up, using transparency, we mix two input images together to produce a new input image. The amount of contribution of each image is controlled by the constant lambda. The new label is also a weighted mix of the two labels. Cut mix uses the same concept as mix-up. Instead of blending the whole image, a mask M is used to filter out a region from the first image. This is superimposed on the second image. This image illustrates supervised training with cut-out. The transformed input image is used with its corresponding label. This is the typical supervised learning with data augmentation, which improves model generalization. Data augmentation can generate an infinite number of new input and label. It consumes only a small amount of computing resource. The question is, are we getting the most out of data augmentation? Why not generate a pair of new input label and force the model to have the same prediction? This is the concept of AgMax. This figure illustrates supervised learning with AgMax. No changes in the model architecture. Since we have a pair of inputs and labels, we also have corresponding pair of model predictions. These predictions must agree since they both refer to the same input. What changes are then needed? This is the standard cross-entropy loss in supervised learning. The difference is the additional agreement loss term weighted by a constant delta. What agreement loss functions can we use? We have mutual information, MSE, KL divergence, and cross-entropy. Side by side, AgMax is superior compared to label smoothing. Label smoothing is fine for standard data augmentation, but fails to significantly improve the model performance when more advanced data augmentations is used. Meanwhile, AgMax works on all types of data augmentation. On ResNet 5090 epochs on ImageNet 1K, using MI as the agreement function, the orange and red bars show that when AgMax is applied, the accuracy improves significantly. The best performance is on mix-up at 77.6%, which is 1.1% higher compared to its version without AgMax. This table shows the improvement in accuracy for MI, MSE, and KL. We also conducted ablation studies on improvement on object detection, instant segmentation, and robustness when AgMax is applied. See our paper for more results and discussions. Thank you for listening. The code and pre-trained models of AgMax can be found on GitHub.